Welcome to RaWMachines, a journey to discover the most impressive processes around the world. Today we will follow the rebirth journey of wood, from the forests of North America to modern mills, where plywood is born. This is not just a production process, but a story of transformation, where steam, steel, and human ingenuity meet to shape the future of green materials. Let's start right now. Plywood was born from a simple idea: how to maximize the strength of wood without wasting a single fiber. When the first craftsmen in the early 20th century began cutting wood into thin layers and gluing them together with the grain running perpendicular, they didn't realize they were starting a revolution. That multi-layered structure, the ply, makes the panel stronger, lighter, more flexible, and warp-resistant. From then on, plywood became a foundational material for the modern world. In house walls in Oregon, in ship cabins in Helsinki, in overpasses, and in the interiors of cities. Every plywood sheet is the result of a long journey, from the deep forest to the factory, from living sap to synthetic glue, from natural wood grain to engineered structure. It is a cycle, both industrial and biological. And to better understand the process of creating this product, join me at our first location, the deep forest, where precision forestry technology and environmental ethics meet. The forests stretching across hundreds of hectares in Oregon, Washington, or British Columbia, where Douglas fir and Sitka spruce trees soar over 50 meters tall, are the lifeblood of the North American timber industry. Here, humanity and nature are not adversaries, they are symbiotic. The harvester machine looks like a steel beast with a long hydraulic arm and a high-speed rotating saw head. In a single fluid motion, it grips the trunk, cuts it cleanly, strips the bark, and neatly stacks the log on the ground. Everything happens in a matter of seconds, tidily and with absolute precision. When the tree falls, the story seems to end, but in fact, it has only just begun. Logs weighing tons are lifted onto trucks, tightly secured with steel cables. On each trunk is a small barcode, containing its entire journey, harvest date, GPS location, tree species, and intended use. Not a single log is anonymous. The modern forest management system has turned the entire industry into a living data chain. The path back to the mill is more than just a physical journey. It is a transformation from nature to industry. The wood is still raw, smelling of resin and soil. But in just a few hours, it will enter a different world, where steel, steam, and algorithms will work together to re-engineer it into a new product that is lighter and more durable. When the wood is brought to the mill, the first step it must undergo is softening. The goal is not to clean it, but to change the nature of lignin, the natural glue that binds the cellulose fibers in wood. Under temperatures of about 80 to 100 GOC, the lignin begins to soften, allowing the log to become pliable and bend without cracking. Engineers control the system via a digital screen, fine-tuning the temperature and time for each wood species. A small deviation could result in the loss of tens of square meters of veneer. The hot water soaks into every fiber. The warmth makes the wood breathe, releasing a distinct resinous scent, the aroma that any craftsman recognizes as the smell of the beginning. After being softened, the logs are cut to precise lengths, typically 8 feet, the standard for a 4-oxide-8 plywood sheet. The industrial saw operates like a surgical knife, its gleaming steel teeth dividing the log into uniform blocks. A laser scanner measures each block, recording data on length, diameter, and moisture content. In an instant, a forest tree has transformed into a factory object, ready for the next process of peeling its natural structure. Veneer peeling. This is the soul of the entire process. The wood blocks are secured onto a giant spindle, the veneer lathe. As the spindle rotates, a long blade, several meters wide, glides across the wood surface, peeling off thin, uniform strips like a rolled sheet of paper. A single log can produce hundreds of meters of thin veneer in just a few minutes. The thickness is controlled by a sensor system. Some are as thin as 0.6 millimeters, others up to 3 millimeters, depending on the application. The veneer sheet unfurls from the log like its own timeline, each roll representing a year of age. This is the moment the wood loses its old shape but retains its soul. The freshly peeled veneer sheets are still soaking wet, soft like fabric. They are passed through a drying tunnel several dozen meters long, where a continuous flow of hot, dry air moves. Sensors measure temperature, humidity, and airflow speed. The system self-adjusts to maintain ideal conditions. The goal? To reduce the moisture content from over 30% down to 6 to 8%. This drying process determines the stability and lifespan of the plywood. If too fast, the wood will crack. If too slow, it will mold. In advanced mills, energy from exhaust gases or recycled steam is reused to reduce consumption. The science of drying is not just about heat, but the art of balancing patience and precision. After drying, each veneer sheet is passed through an automatic scanner equipped with cameras and lasers. Software identifies knots, cracks, core voids, and discoloration. Perfect sheets are designated for the outer face plies. Sheets with minor defects are routed to the inner core layers. Skilled craftsmen still play a role. They use small knives to patch defects with plugs, wooden inserts, or synthetic filler. Each action is a human touch amidst the machinery, reminding us that quality comes not only from algorithms, but from the eyes that have seen wood their entire lives. Next, the veneer sheets are moved onto the layup table. Each sheet is uniformly spread with a thin layer of adhesive, glue, the formula depending on the thickness and wood species. They are then stacked with the grain running perpendicular, JO, between the layers, creating the characteristic cross-grain structure. The physical principle here is simple yet miraculous. The perpendicular wood grains counteract deformation, making the plywood panel lightweight, stiff, and dimensionally stable. Each layer represents a different direction of force, combining to create a synergistic strength. After being stacked, the veneer assembly is transferred to the cold press system. Under light pressure, the layers are temporarily compressed for a few minutes, which helps the adhesive spread evenly, eliminates air pockets, and fixes the position. Cold pressing does not create a chemical bond, but it ensures all layers are set and ready for the hot press stage. Now it is time for heat and pressure to do their work. Giant steel platens are heated to 140 degree, 170 degree rounds, and pressed down onto the stacked wood with a pressure of 150 to 250 psi. In a matter of minutes, the heat and pressure cause the adhesive to change phase and solidify, bonding the layers into one solid panel. When the press opens, the first plywood sheet appears, flat, smooth, strong, and full of vitality. Finally, the plywood panels are trimmed to the exact standard size, 4.8 feet. The edges are squared, and the surface is smoothly sanded. Each panel is scanned through a final automated inspection system, checking thickness, flatness, moisture content, and adhesive marks. Panels that meet the standards are stamped with their grade, marine grade, structural I, or exterior. This is the moment the wood officially gains its industrial identity. From a log that lay dormant in the forest for decades, it has now been completely transformed. The flexibility of steam, the strength of steel, and the precision of computers combine to create the material of the century, where wood is not just reborn, but upgraded. From here, the story moves into a new chapter, the pioneer mills. Let's visit our first mill, Vantec, where technology and tradition combine powerfully. This is clearly demonstrated in their 1,400 mm high-speed veneer line. Every stage, from positioning and heating to peeling, is completely automated and synchronized. As a result, each veneer sheet produced has stable thickness, a smooth surface, and a sturdy structure. Furthermore, the system integrates the drying and treatment steps right into the production process, saving time and energy and reducing environmental impact. The balance between high productivity and stable quality clearly expresses Vantec's design philosophy: automation while retaining the spirit of craftsmanship, modern yet not losing the identity of the woodworking trade. Remarkably, Efficiency and sustainability are always prioritized. The line is designed to maximize the utilization of every log, minimize waste, and thereby protect natural resources. In a world where sustainability has become a responsibility, every veneer sheet here is not just the result of technology, but a tribute to the forests. Standing before this machine, one cannot help but reflect on the journey the timber industry has taken, from the manual axe and primitive saw pit to these automated lines capable of producing thousands of panels daily. That story is an epic of progress, written in wood. And from here, the journey continues to expand. We will turn north to Finland, where the philosophy of sustainability and technical precision are integrated into a long-standing forestry tradition. Mine and Group will demonstrate how a nation turns its forests into a bioeconomy, where every piece of wood is fully utilized and the energy returns to nourish the very forest that gave birth to it. The Pacific Northwest has long been known as the cradle of the U.S. timber industry. The vast forests and a labor tradition closely tied to nature have formed the foundation for generations of families living by the woodworking trade. Among them, the Swanson family is an iconic example. Following a devastating fire in late 2014, they chose Japan's Mainan veneer peeling line, one of the industry's most advanced systems, to rebuild the Springfield mill. During the presentation of the new facility, Chairman Steve Swanson asserted that this was the most sophisticated and advanced plywood plant in North America, highlighting its superior advantages: high veneer quality, the industry's highest wood recovery rate, exceptional labor productivity, and a suitable investment cost. The main line at Springfield is an engineering marvel. The entire system is over 350 feet long, housed within a mill that stretches up to 1,000 feet. The system was fully assembled in Japan, then dismantled, shipped, and reinstalled in Oregon, a process demanding high precision and skill. The fully automated mine and veneer peeling line comprises 7 main components. Let's take a closer look at these components and how they work together. The journey of a log inside the Springfield mill begins at the pre-charger. Here, the log is lifted and held securely while cameras and lasers scan its entire surface. In just one rotation, the system knows exactly where to position the knife blade to cut the most and the best quality wood. Once the data collection is complete, the pre-charger gently rotates the log to the precise center position, then feeds it straight into the lathe. You can imagine it like a robotic arm, neatly placing the log onto the cutting table, ready for the main stage. At the main and lathe, the log begins its transformation. The knife blade peels off thin layers that curl like silk ribbons. This is the veneer, the main raw material for plywood. The main end machine uses hundreds of small spiked discs, or drive spindles, distributed evenly around the log. This drive method keeps the log rotating steadily, preventing slippage and reducing cracking. As the log diminishes, the machine continues peeling until the core is only about 2 inches in diameter, utilizing almost every fiber of the wood. As the veneer exits the lathe, automatic sensors immediately check its quality, measuring moisture content, detecting defects, and sorting it right on the spot. The sheets that meet the standards are moved to the cutting stage. Double blades split the veneer into 2 sheets, each 4 feet wide. Then the rotary cutter processes the edges and cuts them to the required precise dimension. To ensure operator safety, the line features an automatic knife changer, which replaces the blade in minutes without prolonged machine downtime, ensuring both safety and productivity. The cut veneer sheets are then directed to the stacking system. When a stack is full, the floor automatically lowers, and a forklift will carry them out for the next stage. The scrap or defective veneer is not discarded. The waste gate automatically separates them and routes them onto a conveyor belt lying flush with the floor, a cleaner and safer method than traditional practices. Small pieces, veneer tails, or uneven sections are sent to the 2 main splicing machines. There, they are trimmed at the edges, adjusted for thickness, and joined using a special heat-resistant tape, forming 4x4 feet square panels used for the inner core of the plywood. Thanks to this, almost no material is wasted. Everything is reused. The incredible thing is that the entire line, which stretches over 100 meters, only requires 3 operators. The rest is handled automatically by sensors, computers, and mechanical arms. Thanks to this high level of automation, the mill produces veneer with a smooth surface, stable thickness, superior productivity, and a reasonable cost. Springfield, therefore, is not just a mill. It is a symbol of the fusion between art, science, and humanity. There, every plywood panel becomes a story of convergence between the forest and the city, between memory and the future. And it is in this very fusion that we recognize the profound beauty of modern industry, a beauty born from tradition, nurtured by technology, and perfected by human pride. From the refined space of Myllykoski in Finland, our lens crosses the ocean to northern Canada. Here lies a small town named Hearst, dubbed the forestry capital of Canada. The people of Hearst don't just live off the forest, they live with it. From father to son, from grandfather to grandson, the craft of woodworking has been passed down through generations as part of their heritage. The small sawmills of the past have now become modern production facilities, yet the spirit of respect for the material and the trade remains. In the Hearst mills, veneer production is the core process. Logs are softened with controlled steam and heat, then carefully peeled into thin sheets called veneer. The veneer sheets are then slowly dried in hot air drying tunnels. The goal is to reach a moisture content of 6 to 8%, the perfect level for uniform adhesive bonding without causing shrinkage. All parameters, temperature, airflow, drying speed, are monitored by computers, but workers still manually check each batch by hand feel and by listening to the sound when the veneer bends. From these perfect veneer sheets, the journey continues into the plywood manufacturing stage. Multiple layers of veneer are stacked perpendicularly, bonded with waterproof resin adhesive, and then pressed under high heat and pressure. The result is a stable, durable material that can withstand humidity, temperature, and heavy loads. But the mills in Hearst don't stop at conventional plywood. They go further, stepping into the field of modern engineered wood with a specialized product, Laminated Veneer Lumber, or LVL. LVL is the combination of wood's beauty and material science. With its parallel grain structure, it has a strength equivalent to, and even surpassing, light steel in some applications. Engineers use LVL in beams, headers, trusses, floors, and load-bearing walls, where stable load capacity and high uniformity are required. Unlike natural lumber, LVL does not warp, crack, or contain weak knots. For modern builders, it is a material that is both strong and reliable, a perfect block of wood engineered by technology. As this chapter closes, we see the complete arc of the wood's journey, from sapling in the deep forest to the mill to boards, and then transformation into house frames and structures. Hearst reminds us that wood is not just a material, it is the memory of the earth, the intellect of human hands, and a testament to the infinite regenerative capacity of nature. From a tiny seed in the forest to the finished plywood sheet on the production line, the journey of wood is a story of transformation. Every log that is cut is not the end of life, but the continuation of a cycle. The forest creates the material in turn nourishes human life, and humanity, when done correctly, gives back to the earth. At Vantec USA, we witness the power of high-speed technology, where robots, sensors, and data combine to peel every layer of wood. At Swanson, Oregon, we see the art of patience, where steam, time, and human hands together create perfect wood panels. And in Hearst, Ontario, Canada, we encounter the harmony between tradition and engineering, where wood is reborn into structural materials with strength comparable to steel. These three stories all converge at one point: respect for the wood, and through it, respect for nature itself. Today, as the world discusses sustainability, green energy, and new materials, wood still stands as a witness to both eras, the natural and the industrial. It is not obsolete, it merely changes shape to fit the era and human ingenuity better. Thank you for listening to the end of the story. If you also enjoy similar videos, please hit the like button, share, and subscribe to the channel so you don't miss any fascinating stories to come. RaWMachines says goodbye and see you next time.